Hi everyone, welcome back. Today we're going to be working on the next section, which we're still working with sequences and series. And today we're going to work on absolute convergence and the ratio and root test. So, in the grand scheme of things, these are the last two tests that we have to develop for series whenever we want to determine whether these series will converge or whether they will diverge. Alright, now the first thing that we're going to talk about in this section though is going to be absolute convergence. So on the screen here you'll see here that I've color coded in orange that says do the series converge. Alright, now after a little analysis here we'll see that these two series here are both geometric series. So I'm just really quickly going to write that down, that they're both geometric series. So both geometric. Nice. So both of them are geometric series. So what I'm going to do is I'm actually going to extract what their common ratio is then. Alright, so for the first one I'm going to look at the common ratio here, and again the common ratio is the absolute value of that ratio. So the absolute value of that ratio is just going to be 1/4. Alright, so what we're going to do is we're now going to establish, does this converge or does this diverge? Well, because the common ratio is less than 1, that series is now going to be convergent. Alright, well what about the other series? Well, this other series, does it converge or diverge? Now, common ratio here, again, common ratio, I'm going to look at my absolute value for that ratio, which is 5/4. But in this particular instance, 5/4 is greater than 1, which means this series here diverges, or is divergent. So as we start looking at this, we come up with a certain conclusion to say, hey, at the end of the day, these minuses and these pluses, where it is alternating, it does tend to affect whether it's going to converge or whether it's going to diverge. However, look at this alternating series here. This alternating geometric series was not convergent, it was actually divergent. Even though they kind of resemble one another, the first series actually converges, and we'll be able to see that it is actually going to be absolutely convergent. Alright, so we need to define that, and we need to define what it is. Because as we see here, well, could the series be divergent or convergent? Well, we need to do a little bit more work to develop what it is that we're going to be observing. Alright, so I need a few definitions in order to proceed in this section. Alright, so here we are. Now, I have a few definitions here. The first definition says that the series A sub n is going to be called absolutely convergent if the series of absolute values, in other words, this series here where all of the terms are positive, is convergent. Alright, so that term, absolutely convergent, we must definitely remember that. We must definitely have that ingrained in us. Secondly, is it conditionally convergent? A series is called conditionally convergent if it is convergent but not absolutely convergent. Alright, so if a series converges, but then if we look at the absolute value of all of the terms and that does not converge, it's okay. All we're going to say is that that is conditionally convergent, as long as the original series did converge. Alright, now using both of these definitions, we actually get this really nice theorem that we're going to be looking at, which is called the Absolute Convergence Test. Now, some books mention this as a test, others mention them as a theorem. However, I always like to consider this a test because, again, at the end of the day, we are testing to see whether a series is convergent or divergent. Now, in this particular instance, it says that if a series is absolutely convergent, then it is convergent. Now, that one is huge. Huge, huge, huge. Because that now tells us that if we go through and if we just check the absolute value for this specific series, then we should be able to determine whether it's going to converge or not converge. All right? And that's what we're looking at with this specific instance. All right? Which again is going to be very, very nice. So, keeping this absolute convergence test in our back pocket, this kind of gives us another method or another way to kind of analyze these alternating series, right? Because in the previous sections we were looking at the alternating series, and within those alternating series we were then analyzing, do they converge or not? And in this particular instance we just get something else to add to our toolbox, another tool to determine whether these series are going to converge. Now that we have that, let's go through and let's try a few examples just to get our feet wet to see what is happening here. All right, so here is what we're working with. So this says that we need to determine whether or not the series is absolutely convergent or conditionally convergent. And the series that we're working with here is going to be the series with n beginning at 1, tending towards infinity, for the explicit formula of -1 to the power of n minus 1, all divided by the square root of n. Alright, so we need to determine whether these series are going to converge absolutely or whether they're going to conditionally converge, one or the other. Which means we need to check two different types of convergence here. Alright, now the type of convergence that we first need to check is going to be the absolute convergence. Alright, so what I'm going to write here is that I'm going to say first, check the absolute for that series. Alright, so that's the first thing that we're going to do. So coming over here, what I'm going to do is I'm just really quickly going to take this series here and I'm going to start doing that check that I just said here that we want to do. Alright, so let's go ahead and let's put it here. There we are. Now let's go ahead and let's make that blue. Perfect. Perfect. So now I want the absolute value of this series here, so I'm just going to slap on an absolute value on here. There we are. Now when we work with the absolute value of this series, I want you to then analyze. As n starts progressing, what we really have here is just going to be that series once again, and let's put this on here, is going to be that series once again. There we are, just like that. And hopefully I can finish my thought this time. There we are. Let's change the color. Beautiful. Now what we're going to have is that series with an altered numerator. Because the absolute value is here, it's going to prohibit this series from alternating, meaning every single number is just going to be the numerator of 1. Because again, if it's ever -1, then the absolute value takes it and becomes a 1. Alright, so we now then need to look at this series. So let's start looking at this series here. What does this series do? Alright, well let's go ahead and let's rewrite it slightly different. How about we now rewrite this as the series n beginning at 1 to infinity for 1 over n to the power of 1/2. Would you agree that this is a p-series? That's good for us because we know stuff about the p-series. Alright, so what do we know about the p-series? Well, we know about the p-series that the p-value here is going to be 1/2. Any value that is less than 1 will cause this to diverge, which means this series here diverges. So I'm going to say at this point in time that this series, the one that we're analyzing right in here, let's copy that over. Let's put it right here. There we are. This series diverges. Now remember, every time that we're telling or that we're giving that a series diverges or converges, we must give the reasoning. Well, this diverges because it is a p-series with p being 1/2. Alright, so we ran into our first kind of snag here, that when we looked at the absolute value of all the terms for that series, it does not converge. It actually diverges. So now, when we come over here, we then say, okay, well, it's not absolutely convergent, so that's not going to work. Right? Now, we know that the absolute value of all of the terms for that series diverges. Well, does this series, so now does the original series converge? So now is when we need to go back into the alternating series test and determine, does this series now converge or not? Alright, so we're now going to continue with that test. So I'm going to write down here, now continue with the alternating series test. And I hope you all don't mind, I'm going to abbreviate this as AST. Alright, so let's go ahead and let's look at the alternating series test. Using the alternating series test, we need to determine two things. Alright, or we need to determine a few things. Number one, we need to determine that a sub n is non-increasing. Alright, that was one of them. And the second one, we need to determine that the limit as n tends to infinity for a sub n must be equal to 0. If we have both of these conditions met, well then we're going to get that this series, this alternating series, is going to converge. So let's go ahead and let's start then analyzing that. Alright, so now what I'm going to do is saying this. I'm going to use, oops, excuse me there. I'm going to use my original series here. Let's put it here, there we are. Alright, let's move it a little bit higher. Whoa. Yeah, technology is still working with it, you know. It's a work in progress. Alright, there we are. So using this series, I'm going to identify a sub n to just be my value for this 1 over n, or 1 over square root of n. Alright, now we must make sure that these values are non-increasing, so this is going to be my, call it f sub n. Alright, so f sub n in this particular case looks like n to the power of negative 1/2. So if we go ahead and if we take a derivative here, f prime, then we're going to get negative 1/2 n to the power of negative 3/2, which then turns into negative 1 over 2 times n to the power of 3/2. Now this here, n values, the n values can only be greater than 0 because we're going to have this original function. So the domain for this original function must be that n is greater than 0. if that's going to be the case, well then n greater than 0, that's going to be kind of nice, because then it's going to tell us that all of these values are going to come out as negative, which means they're always going to be decreasing, which is exactly what we want to see, because again, we want that it is non-increasing. Alright, so anything to the right over here, and again, non-existent on the left, but on the right-hand side is where we have all of these negative values, which means it is always going to be decreasing. More specifically, it's going to be decreasing for n being equal to 1. So as long as I have n is equal to 1, this is always going to be decreasing, which is nice, because again, I already met my first condition. So a sub n is non-increasing by the first derivative test. Nice. Alright, so we got that done. Now we need to check the limit. So let's go ahead now and let's check that limit. Now we're going to check the limit as n tends to infinity for this a sub n, and a sub n is just 1 over the square root of n. Now this limit is actually a really nice direct application here, that when we take this limit, as n gets large, because it's in the denominator, it's automatically just going to tend to 0, which is really good. Now that we got this, I'm going to say here also the limit as n tends to infinity for this 1 over square root of n is equal to 0. Met that second condition. Therefore, by the alternating series test, this series here is going to converge, which is really nice. Alright, let's go ahead and put it right over here. There we are. Alright, let's color it blue. There we are. Perfect. Therefore, by the AST, the alternating series test, the series converges. Alright. So, nice. Alternating series test tells me that this converges. However, the absolute value for all of the terms tells me that it diverges, which means this does not converge all the time. So it is not absolutely convergent, which means there's only one thing else to say. Thus, the series is conditionally convergent. And that's all there is to it, right? All we need to know is, based on our previous techniques, will this series converge, or will this series converge, or will this series diverge? All right, with the small added caveat that we still need to test the absolute value of those terms. That way we can come to a conclusion of absolutely or conditionally convergent. So let's check out a different question here. This question here is going to be the series of n beginning at 1 for negative 1 to the power of n, all divided by n cubed plus 1. Alright, so let's go ahead and let's check this series. So again, the first thing that we're going to do, I'm going to say here first, we want to check the summation or the series of all of the absolute value of all of the terms. So let's start looking at that then. So let's go through and consider that. Negative 1 to the power of n, all divided by n cubed plus 1. This needs to be the absolute value. And again, when we take the absolute value of this function, that's going to cause this function not to alternate, which means this numerator every time that it's -1, it's going to be automatically converted to the +1. So in that instance, all of my numerators here are always going to be 1. Denominator, it's just n cubed plus 1. Now that's kind of nice, because now I'm looking at this series here, and all I need to determine is, does this series converge or does that series diverge? So that's a big question now, and let's see if we can then analyze that question. Well, I kind of only see one variable here, and that variable's in the denominator, which to me that is real nice. So what I'm going to do here is I'm going to proceed using a comparison. So if I'm using a comparison here, I'm just going to go through and use a comparison test to determine whether this converges or diverges. So that's going to be kind of nice. Let me extract here my my function. It's n cubed plus 1. Again, I just need to figure out what I need to pull back on, what I need to eliminate from this function, and all the things that I want to eliminate are all of the constants. So let's try to eliminate all the constants, all the coefficients, and just leave the variable and its exponent. So what I want to do here is I just want to look at 1 over n cubed. Now, which function is larger? All right, so that's where we need now to come to a conclusion here. All right, so since this function on the left has a plus 1, this denominator will be larger. In other words, this function overall fraction is smaller, which means 1 over n cubed by itself is larger. All right, that's pretty good. So this here, this function here, is actually your p-series. Yay! We found a p-series function once again. Well, what's the p-value here? That p-value is just p is equal to 3, which means this is greater than or equal to 1, so we're going to be divergent. Nice. So let's go ahead and let's write up that comparison. All right, so I'm going to say here, so the initial series that we're looking at, n cubed plus 1, is less than this series here, and beginning at 1 for n cubed, and this series for 1 over n cubed is convergent because it is a p-series with p being equal to 3. Then I'm going to say thus, this initial series, and it's equal to 1 over n cubed plus 1, is also convergent by the comparison test. All right, so again, as we're structuring this argument, we're going to say, okay, well, let's check the absolute value of all of the terms. Once we get that, we can use whatever formula we have there, whether it be geometric, whether it be telescoping, whether it be partial sums, whether it be comparison, limit comparison, whatever it may be. We're going to use all of our knowledge to determine, does this converge or not? All right, once we identify that it is, in this case, divergent, then we're going to say, okay, well, that's going to be nice, right? Or sorry, I put divergent, and it's actually supposed to be convergent because my p-value is greater than 3. My sincerest apologies there, everybody. So this is convergent. I have no idea why I wrote divergent. There we go. So therefore it's convergent by the comparison test. Perfect. So once we use all of those techniques that we've developed, we can now say, hey, this comparison that we have here, and again, I'm illustrating that comparison, not just with the functions, but I'm comparing that series with this other series that I developed. The conclusion that I have is that the series that I found is convergent, but since it bounds the initial series from above, if the above function converges, then by the comparison test, the bottom function must also converge. All right, so what does that tell us now? Well, that tells us that this function is convergent. Therefore, the absolute value, -1 to the power of n, for n cubed plus 1, where n is equal to 1 to infinity, is absolutely convergent. And we could say it's absolutely convergent, and let me erase that comma, it doesn't go there, by the theorem that we were just looking at. That theorem is the absolute convergence test. So I'm just going to say here, by the absolute convergence test. There we are. So again, if we see that when we take the absolute value of all of the terms for that series, if that series converges, well then that's going to tell me it's absolutely convergent, because if it converges with all the absolute values, typically when you remove the absolute value, it's still going to converge, and that's what that absolute convergent theorem told us. So that's really nice to then start observing that we can start developing a lot of these methods to start looking at these series to determine whether they are convergent, or whether they're absolutely convergent, or whether they are conditionally convergent. Nice. So let's now look at a different example. That different example that I want to see now, this is going to be part C, is going to be this series where k is equal to 1, and this is going to be -1 to the power of k multiplied by tan inverse of k, all divided by k cubed. Alright, so again, we see alternating, so that's going to be one of the first observations that we see. Anytime that we see alternating, my quick conclusion here, or my quick observation, is to always check the absolute value of that series. Alright, and sorry, the absolute value of the terms of that series, and let's see what's happening there. Are we going to be able to make this conclusion that this is going to converge? If it does converge absolutely, then that's awesome. Converging absolutely means that we are going to be convergent. So let's now start dissecting this. Alright, I have k is equal to 1. This is going to be to infinity, absolute value, -1 to the power of k, tan inverse of k, all divided by k cubed. There we are. But again, since I'm working with the absolute value, it's going to make this alternating piece non-existent, which means if it makes it non-existent, then that's going to be very, very beneficial to us. Here we are, so that's k is equal to 1, and then this here is just going to be tan inverse of k divided by k cubed. There we go, not too bad. Alright, now we must then start analyzing this function here. So tan inverse of k divided by k to the power of 3. Let's go ahead and let's extract. Well, what can we use? One of my favorites is going to be this comparison, or you can do a limit comparison, whichever one you deem useful. I like a comparison, and the comparison that I want to use here is this comparison that I'm going to ask you to recall really quick, that tangent inverse of theta is actually bounded below by negative pi halves, and it's bounded above by pi halves. Alright, so I believe I've shown this depiction a while back on one of my other videos. I know it dealt with sequences in series, but at this moment it escapes me as to which section that actually was that I depicted this. Alright, so if we have, here we go. I'm going to make sure I draw my asymptotes here. Alright, so I have my asymptotes here, and my function for tan inverse looks like this. So what we're looking at here when we're analyzing this is that we're saying that tan inverse is actually bounded, and it's bounded by pi halves and negative pi halves. And again, that's true because, again, we always bounded tan inverse to be this one-to-one function, and this is the bounding that occurs. When we do this, again, I want to use this now to build a comparison for this. So let's use a comparison now. So if I have tan inverse of k divided by k cubed, well, I know that I can bound this from above by using this upper bound. So tan inverse of k is now bounded from above by pi over 2, but then I still have this k over 3 dividing it. Alright, we could get a lower bound here if you wanted to, and that's perfectly fine. So if you want to on your off time, you could definitely try that and see what you then get. Alright, but in my particular instance, I just want to keep this as is. I want to use this particular piece here. Alright, so let's see what this is equal to then. This is just pi divided by 2 k cubed. Alright, not too bad. Alright, so let's now try to extract this specific comparison. Right? I actually want to write this slightly different, and I actually want to write this like this. And now, why do you think I want to write it that way? Well, I want to write it that way because we found a p-series. Yay! It's a p-series where p is equal to 3, which means this will converge. Alright, that's nice. So all I need to do now is write it up, because now I know that this series here is going to converge by a comparison. So let's go ahead and let's write all that out. Alright, so let's start writing it up. So here we are. So I'm going to say here, so this series where k is equal to 1 for tangent inverse times k divided by k cubed is less than this series, k beginning at 1, for pi halves 1 over k cubed. Alright, by that comparison. And we're also going to say that this series, the one that we're using to compare, pi halves and 1 over, and you know what, let me write this differently, that way you can see it a little bit more clearly. It's a bad sigma. Alright, pi halves is a constant, so it just moves out of that sigma. And so here again, this is where we have that p-series. So this series here is convergent is convergent because it is a p-series with p being equal to 3. Alright, that's nice. Thus, the initial series that we're observing, remember that absolute value part, thus this series is also convergent by the comparison test. Alright, nice. So now that we've developed this whole process to say, hey, the absolute value of each terms for that series makes that series converge, therefore it's going to be absolutely convergent. So therefore, the series that I am looking at, where k is equal to 1, negative 1 to the power of k times tan inverse of k, all divided by k cubed, is absolutely convergent by the absolute convergence test. And that's all there is to it. We developed, or we found, that this is absolutely convergent. Alright, and that was that part there. And again, we must go through and we must state anything that we are using, any test that we develop, any items in our toolbox that we're using to make sure that this series will converge or it will diverge. Alright. So now that we know about that, let's go through and let's start analyzing what is going to be the ratio test and what is going to be the root test, and how and when do we use them. Alright? So alright, ladies and gentlemen, so here we're going to be motivated by this question down below that says, does the series converge or diverge? And that series here is the series beginning at 1 going towards infinity, where the variable here is going to be n, and if you notice the numerator we have n factorial, the denominator we have 3 to the power of n. So just as a really quick reminder, n factorial really just starts with n, then it's multiplied by n minus 1, then it's multiplied by n minus 2, and then we just keep on deducting 1 from the previous term all the way till we multiply 2 times 1. Alright, that's the way that we multiply, or that we use factorials. Now, as a general rule, we also use that 0 factorial is equal to 1. Alright, so we must remember those rules from algebra class in order for us to determine whether these series are going to converge or diverge. Now, within all of the previous methods, we have not had the variable be in the exponent and there be a factorial in the mix within this explicit function. So what we're going to do now is we're going to need to develop a new test that will allow us to work with series that have a factorial or that have the variable in the exponent as such. One of the methods that we use is this ratio test. We're going to be looking at the ratio test, and we're going to be looking for 3 different outcomes. We're going to want to take a limit of the absolute value of the next term in the sequence, or in this case, using the explicit formula, the next term in that explicit formula divided by the original explicit formula. We want all of this to be in the absolute value, that way we don't worry about positives or negatives in the mix. Now, if this limit as n tends to infinity is equal to 1, then the very last case is going to say that the ratio test is inconclusive. What that means is that the ratio test tells you nothing. It means that the series can either converge or it can diverge. It means that the ratio test does not know. And if it does not know, then you must go to different tests in order to figure that out. Now, if the limit is if the limit is L and L is less than 1, well then the series is going to be absolutely convergent. And you remember, if the series is absolutely convergent, well then it's convergent. So that works great. This is a very powerful test to say, or to completely say, that it will be absolutely convergent. Now, what if the limit is greater than 1? So if the limit is any time greater than 1, or if the limit is infinity, so greater than 1 or if it's infinite, then the series is going to be divergent. Alright, now this is a first test that actually gives us that a series is convergent or is divergent. The divergence test just tells us that the series will be divergent. Doesn't tell us anything about convergence. The alternating series test tells us that a series is convergent, doesn't tell us anything about being divergent. Alright, this is one of the only tests that actually give us that if we find a limit, we will be convergent, or if we find a limit with a specific value or an infinite value, then it's going to be divergent. Now, we want to use this in this specific example here. Alright, one of the examples here that says, use the ratio test to determine whether the following series is convergent or divergent. Awesome. So what I'm going to do really quick is I'm just going to identify what is my A sub n. Alright, what is that explicit formula that I am working with? So A sub n in this particular case, or you know what, we could say A sub k, simply because we're using the k values. So my A sub k is just going to be k to the power of k divided by 2 to the power of k. So again, it's just the original formula that I'm given. Now, I'm also going to denote A sub k plus 1. Now, A sub k plus 1, this is just the extra term that we get once we add 1 to this specific formula. So, my numerator now becomes k plus 1 to the power of k plus 1. Alright, again, I'm putting a k plus 1 on a k plus 1 divided by 2 to the power of k plus 1. Very nice. Alright, this is awesome now. All I have to do now is I need to take a ratio here, and I need to take the absolute value of that ratio so that I can then start looking at my limit. So, let's go ahead and let's start working with that. Alright, and remember, all of this is for k being greater than 1. Alright, so here we go. So now, when I look at my limit as k tends to infinity, for the value of a sub k plus 1 divided by a sub k, this is going to be the limit as k tends to infinity for my numerator, which was this a sub k plus 1. So that's going to be k plus 1 to the power of k plus 1 divided by 2 to the power of k plus 1. Whoops. There we are. Big division bar. That's a big division bar divided by a sub k, which is k to the power of k divided by 2 to the power of k. There we are. Alright, looking pretty good so far. Now, we have the absolute value. In this particular case, we can kind of argue our way to say that we don't really need the absolute value because all of these terms are just going to turn out to be positive. Alright, so what I can do here is I can either move the absolute value to the outside of the limit, or I can just say, since k is going to be greater than 1, this is always going to be positive, we can eliminate that absolute value. Alright, so I'm going to go through and I'm going to simplify some of these items. Alright, so I have k plus 1 to the power of k plus 1, all divided by 2 to the power of k plus 1. Now, I want to actually do something differently here. Ouch. There we go. Now, what I want to do differently is this denominator, 2 to the power of k plus 1. Now, I'm going to show you here that 2 to the power of k plus 1 is really just 2 to the power of k times 2 to the power of 1. Because when we multiply the same base, we actually keep the multiplication between those two terms. So this denominator turns into 2 to the power of k times 2 to the power of 1, multiplied by the reciprocal of the denominator, which is 2 to the power of k, divided by k to the power of k. Right, it's not looking too bad now. It's not looking too bad. Why is it not looking too bad? Well, what do you notice about these 2 to the power of k's? Yep, you guessed it. They're going to cancel out. So we can go through and we can say, hey, by the way, these guys are going to cancel. So it's looking even better. We get the limit as k tends to infinity. There we are. Now we're left with this numerator. Alright, k to the power of 1 to the power of k plus 1. Divided by, I have a constant here. So that's going to be 2 multiplied by k to the power of k. Awesome. Alright, awesome. Now, another trick that I'm going to do is I'm going to use that exact same process again, but this time I'm going to use it for k plus 1. Notice that k plus 1 to the power of k plus 1 is really just k plus 1 to the power of k multiplied by k plus 1 to the power of 1. When we have the same bases multiplying each other, then the exponents just add together. So, if I'm looking at this as the limit as k tends to infinity, for my numerator now, my numerator is going to be k to the power of 1 to the power of k multiplied by k plus 1 to the power of 1. Then this now leaves me with 2 divided by k to the power of k. Now this is really nice in this particular instance. Alright, so just really quickly I'm outlining what I'm doing here. There we are. Awesome. Now watch what's going to happen here. The limit as k tends to infinity. Let's make that k there. There we are. Alright, so notice, numerator I have a variable to the, I have a base to the power of k. Denominator I have a base to the power of k. So what I'm going to do at this point in time is I'm going to say k plus, oops, excuse me. I'm going to say I have 1/2. That's going to be my half here. And then I'm going to have k plus 1 divided by k. All of this is going to be raised to the power of k, and that's going to be multiplied by k plus 1. There we are. Alright, looking pretty good. Let's keep going. Alright, so here we go. Now, this middle term actually turns out to be quite nice because that middle term, if we divide by this monomial, then we get 1 plus 1 over k to the power of k multiplied by k plus 1. Now, that middle term should automatically strike up an interest simply because this is one of the important topics that we discussed back in chapter 7 or chapter 6 when we started this course. That topic said that if we take x towards infinity and we analyze then 1 plus 1 over, let's say, x to the power of x, then we get the constant e. Alright, so this is a very, very nice topic here to say, or version here to say, that as we take this limit for that middle term, then we're going to naturally get e. So as we start looking at this, we're going to get 1/2 times e, but then as k goes towards infinity, check out this term here. What is this term heading towards? Well, yeah, that's going to head towards infinity. So here, we naturally get 1/2 multiplied by e, and then that last term is just going to be taking it towards infinity. So now, this is my L value. So, let's go ahead and try to summarize this piece here. I'm going to say, thus, this series, k beginning at 1, k to the power of k, divided by 2 to the power of k, diverges I'm just going to say by the ratio test. So this diverges by the ratio test, and simply because all of the work outlined here tells me, or logically tells me, that my limit will then be infinity here. So as I then start looking at my limit in this particular instance, L tends to infinity, so that means that this series must diverge according to my ratio test, and that's this part right in here. Awesome. So we get that our first example diverges. Well, let's look at a different example now, and hopefully this next example won't diverge, and it'll give us more of a convergence. Here goes part B. So let's start looking at this series as, let's say, n is equal to 1, and this is going to be for 2 to the power of n divided by, there we go, divided by n factorial. Alright, now again, because I'm looking at this series and I'm looking at my explicit function, I have a variable in the exponent and I also have a factorial. That to me then signifies, hey, I probably want to use the ratio test. So let's go through and let's identify what is my a sub n. A sub n in this case is 2 to the power of n divided by n factorial, and I'm also going to use n plus 1 as my a sub n plus 1. This is going to be 2 to the power of n plus 1 divided by n plus 1 factorial. So now as I start thinking of the limit in this particular instance, the limit as n tends to infinity, I need to now consider a sub n plus 1, which was this initial piece. So 2 to the power of n plus 1 divided by n plus 1 factorial, all divided by 2 to the power of n divided by n factorial. Alright, so let's take this limit limit as n tends to infinity. Notice the absolute value doesn't affect this at all, simply because all of the terms in this series here, or in this specific formula, will always be positive. There's no way that we can get a negative number out from this, so we're going to go ahead and just eliminate these absolute values. This is very specific to when we use an alternating series test or anything like that, where a series will be alternating. Then the absolute value becomes very, very crucial for us to be able to apply that limit. So I'm just going to rewrite that numerator. All right, so rewriting my numerator here, I get 2 to the power of n times 2 to the power of 1. Again, that was this numerator here. Denominator here, that's my n plus 1 factorial. Now watch what I'm going to do here. You know what, I'll take it step by step. N plus 1 factorial multiplied by the reciprocal of the big denominator, which is n factorial divided by 2 to the power of n. Alright, one thing that you should notice again is the 2 to the power of n's cancel out, so that's pretty good. That now leaves us with the limit as n tends to infinity for 2 times n factorial divided by n plus 1 factorial. Alright, looking pretty good. Let's keep going, see what else we can do. We're going to try to manipulate this algebraically. That way, at the end of the day, we can wind up with some very, very nice result. Alright, notice the 2 here. What I'm going to do really quickly is I'm going to factor out that 2. There we are. So 2 times that actual limit, and this will be n factorial. So remember the definition for n factorial. That was n times n minus 1 times n minus 2. And then you keep going till you multiply 2 times 1. There we are. Divided by, let's see this denominator. We start with n plus 1, and then we subtract 1 to operate on this to use the operator of the factorial. So subtract 1 from that term, and we just get n. Subtract another 1, we get n minus 1, and we keep on repeating this over and over and over until we multiply 2 times 1. Now, in that particular instance, notice what's going to happen. N minus 1 cancels out with n minus 1, n minus 2, n minus 2, so on and so forth. Everything seems to cancel with one another, and the n's also cancel. Now, that's actually really nice, because this now leaves me with 2 times the limit as n tends to infinity with, or for the fraction of 1 over n plus 1. And it's at this point in time that we can take the limit, and this limit now is going to rapidly condense down to 0. So this will now be 2 times 0, which is just 0. And here's your limit. So here's my limit L. L is in fact equal to 0. Now if L is equal to 0, if that limit is equal to 0, then we go to the ratio test and we say, what does that tell us about my series? Well, that's going to tell you that your series is absolutely convergent. So, I'm going to summarize this, and I'm going to say so. This series, n is equal to 1, 2 to the power of n divided by n factorial, is absolutely convergent by use of the ratio test. That's all there is to it, folks. Just like that. Alright, so now that we have the ratio test under our belt, what I want to do is I want to observe another test. And that test is going to be the root test. So, allow me to write that down, and then we'll go ahead and we'll talk about it in just a bit. Alright, so here is your root test. Now, the root test is going to say something very, very similar to the ratio test. basically we want to take a limit as n tends to infinity. If the limit is less than 1, well then this series is going to be absolutely convergent. If the limit is ever greater than 1, or if it tends to infinity, then the series is divergent. And if the limit is ever equal to 1, well then the test is going to be inconclusive. And I just realized I made a small mistake here. Alright, let's cut that. And we are going to rectify that situation right now. And we're going to say, and L is equal to 1. Then we can say what we had here. Paste it. There we go. Then the root test is going to be inconclusive. There we are. Not too bad. Awesome. So, all we have to worry about is taking the nth root of the absolute value of that explicit function that we're observing. If we can do that, well then, hey, everything's going to be working just fine. So, here goes. We have to use the root test to determine whether the series is convergent or divergent. For the first question, this is going to be the series beginning at 1 tending to infinity, and this is going to be for the explicit function of 2 times n divided by n plus 1, all raised to the power of n. So my a sub n in this particular instance, a sub n, is just the function itself. 2 times n divided by n plus 1 to the power of n. There we are. So when I look at my absolute value in this particular instance, I'm going to say, so the absolute value of a sub n is going to be the absolute value of 2 times n divided by n plus 1 raised to the power of n. But notice, none of these terms will ever get us negative because n is always going to be greater than 1 or greater than 1. So in this particular instance, we don't worry about the absolute value. We can just say, hey, this is the actual formula that we're using. Awesome. Which is just a sub n. So let's go ahead and let's take the limit now. Limit as n tends to infinity for the nth root of the absolute value of a sub n. So the absolute value of a sub n, that's this formula here, as we see there, divided by n plus 1 raised to the power of n. There we are. Now look at what's happening here, the nth root of a formula to the power of n. This means that these guys are inverse operators of one another, which means all we're going to get here is the limit as n tends to infinity for 2n divided by n plus 1. And this we know how to evaluate. We can go back into Calc 1 and divide both numerator and denominator by n to leave us with this. As we take the limit as n goes to infinity, then we naturally just get 2. 2 in this case is my limit L, and in this particular instance 2 is going to be greater than 1, which then tells us that we will be divergent in this particular case. So let's go ahead and summarize. Thus, the limit as n is equal to 1 for 2 times n divided by n plus 1 to the power of n is divergent by using the root test. Isn't that nice? Look at that. Now, this doesn't tell you what the actual summation is. This, again, just works to say that it is convergent or divergent. This is not equal to the sum of this series. All right, very important to analyze that. Part B. All right, part B, we're going to be looking at the summation as k is equal to 1 for k divided by e to the power of k. All right, so again, what I'm going to do is I'm going to identify my a sub k. In this particular instance, it's going to be k divided by e to the power of k, and I'm also going to identify the absolute value of a sub k. In this case, it's just k divided by e to the power of k. Now, could this all ever be negative? In our instance, no, it can't be negative, because again, any k values that are 1 or greater than that will always deem this to be positive, which means we're going to be left with this here. So as we start looking at the limit now, so let's find my limit L. My limit L is going to be, as k tends to infinity, and I'm going to take a kth root of the absolute value of the function, which is just going to be k divided by e to the power of k. So now, as I start taking this limit, k goes towards infinity. Now, I'm going to split this in this form, divided by kth root of e to the power of k. Now notice what happens to the denominator. The denominator here is just e. Alright, that's pretty good. So now I need to worry about this numerator. Alright, so we now have to worry about that numerator, so let's see this. Now remember, e is just a constant, so the constant can factor out, and all we're looking at is the limit as k tends to infinity. Wow, that looks all one big jumbled mess. Here we go. The limit as k goes towards infinity for k to the power of 1 over k. Alright, so we now have to analyze this, and this goes back into the methods that we learned back in chapter 6. We now have to figure out how we're going to evaluate this particular limit. Alright, so I went through really quickly here, and I gave you a quick version of taking that limit using the techniques that we learned back in chapter 6. Alright, so as we then start looking at this limit, we should be able to get that this limit is equal to 1. Now, that's going to be nice, because if this limit here is equal to 1, then that just means we're multiplying 1 over e times 1, which is just 1 over e. And 1 over e, this is the limit that we're looking for, and 1 over e is less than 1. If it's less than 1, well, according to the root test, then less than 1 means that we're going to be absolutely convergent. And if it's absolutely convergent, then that means it must be convergent. So I'm going to say thus, the summation of k divided by e to the power of k is convergent by using the root test. Nice. Look at that. All nice and neat. Very concise. Alright. So that is now going to wrap up this particular section. And again, this particular section we were looking at absolute convergence. We were looking at the ratio and the root test. Alright, so I hope you all enjoyed this particular lesson, and we'll be back for some more lessons shortly.